The paper we're diving into today is called Web World Models, or WWM. And I think it presents a really tectonic shift in how we architect environments for large language models.
It really does. It's a beautifully engineered solution. What WWM does, in essence, is introduce this hybrid architecture that it solves the biggest conflict we have in building these persistent, scalable LLM worlds.
That trade-off, right? The one between control and context capacity.
Exactly, that trade-off. And the way they solve it is by splitting the world state into two very distinct layers.
Right. You have the deterministic physics layer on one side and the stochastic imagination layer on the other.
And the physics layer is, just standard web code. Think TypeScript schemas, database rules.
Yeah.
It's the boring but super reliable part that handles things like coordinates, inventory, logical consistency.
While the imagination layer, that's all LLM. It generates the descriptions, the dialogue, the aesthetic style, all the flavor.
And the result is you get an environment with the robustness of a traditional web framework, but with the effectively unlimited, procedurally generated content of a massive generative model.
Which gets us to the punchline of the whole paper.
Hey,
Achieving object permanence with no storage cost. It's huge.
it's the whole ballgame. Relying on deterministic generation to create an infinite world that stays logically consistent over time. It solves the scalability problem without giving up reliability.
I think to really get why that's so important, we have to talk about that missing middle ground they mentioned. Because right now, anyone building these things is stuck between two extremes.
We really are. If you look at figure 1 in the paper, it lays it out perfectly. On one side, you have, let's call it extreme 1, conventional web frameworks.
Super reliable, robustly engineered.
For sure. But the context is completely fixed. Everything has to be defined by a database schema or a handcrafted API endpoint. So you get high reliability, but you just can't scale the complexity of the world.
And then you swing to the complete opposite, extreme 2, fully generative world models.
Yeah, these are the ones that promise everything. Unlimited context, rich 3D or video environments. But the world is built on pure, unpredictable generation.
Which is a nightmare to debug. And it's incredibly expensive, and you have no structural guarantees. Agents start running into hallucinations, state inconsistencies.
Yeah.
The whole experience just falls apart.
WWM just steps right into that gap. It's the bridge. It uses code, the physics, to set the hard rules, and then it forces the LLM, the imagination, to play within those rules. You get the best of both.
Okay, so let's get into the weeds of that technical split. The total state, CTI, is the physics layer plus the imagination layer. The interaction seems to be the key.
It's everything. The physics layer maintains what they call the symbolic invariance, your inventory, your coordinates, your health points. It's the source of logical truth.
While the imagination layer, that's just handling the descriptions, the narrative, what it all feels like.
Precisely, and the order of operations is non-negotiable. This is the secret sauce for preventing hallucinations. The code always computes the physics layer outcome first.
So if my agent tries to walk through a locked door,
the physics layer processes that action. It checks the state. It says, nope, door's locked. The agent's coordinates don't change. That symbolic truth is established first.
before the LLM even gets a chance to describe what happened.
Exactly. Only after that symbolic state is updated and locked in does the LLM get to synthesize the imagination layer. And it's conditioned on that new updated state. So it might generate a description like, you push against the heavy oak door, but it doesn't budge.
But it can never generate the door magically opens.
It can't. The system forces logical consistency before creativity is even deployed. It's such a simple but powerful architectural choice.
Which leads us right into their 4 core design principles. Let's start with number 1, the separation of concerns. We've been talking about it, but what does it really enable?
It enables structural certainty. That's the term they use. The physics layer is like the immutable game loop in a video game. It's written in normal debuggable code. It handles the logic. You can't spend money you don't have. You can't walk through walls.
And the LLM can tell a great story about trying to walk through the wall, but it can't ever change the rule that says you can't.
Never. That separation is the bedrock of the system's reliability.
Okay, principle 2, typed interfaces as the common language. This feels like a direct attack on the black box problem of deep learning.
It is. I mean, traditional deep learning is all about these opaque high-dimensional vectors. They're impossible to validate. WWM says, no, we're not doing that. The world state is represented by strict schemas defined with TypeScript interfaces.
So if you're generating a planet, the interface demands specific fields like biome hazard and so on.
Right. And the LLM is forced to output a valid JSON object that conforms perfectly to that type.
And that's how you kill what they call structural hallucinations.
Exactly. A structural hallucination is the LLM suddenly deciding an item needs a mood field, or that a planet's gravity should be measured in, I don't know, colors. If the generated JSON doesn't match the schema, the physics layer just rejects it. The types are a filter that protects the whole application.
Or a really strong filter. Okay, now for the big one, principle 3. Infinite worlds via deterministic hashing. How do you get an infinite universe without an infinite database?
This part is so clever. It's just-in-time procedural generation, but with a twist. When you arrive at a new coordinate, say xy, the system doesn't look it up in a database. It takes those coordinates and runs them through a stable hash function.
And that hash spits out a unique, but always the same seed for those coordinates.
Correct. That seed then initializes the LLM's sampling process for that location. Since the hash function is deterministic, the output for xy will always be the same. Every time you visit, you get the same base description.
That's the object permanence. But wait, what about changes? If I build a house or cut down a tree at xy, doesn't the hash just overwrite that the next time I visit?
That's the critical distinction. The hashing only generates the initial ambient background. Any changes an agent makes, building a house, harvesting a resource, those are tracked in a small, finite, and mutable database that's part of the physics layer.
Ah, I see. So when the LLM generates the description for a location,
It's conditioned on two things: the deterministic seed from the hash and any symbolic changes that are logged for that location in the physics layer database.
so you get the consistent base world plus any persistent player changes on top.
Exactly. The canyon is always a canyon, but if you logged bridge built over canyon, the LLM will describe the canyon with your bridge in it. That's how you scale.
That's brilliant. Okay, last one. Principle 4. Graceful degradation. This feels very practical. LLM calls were slow, they're expensive.
Right, this is their fidelity slider. It's pure pragmatic engineering. At high fidelity, you're getting real-time, bespoke LLM generation. It's amazing, but costly.
And if the budget gets tight or latency spikes.
The system can slide down to medium fidelity, which just pulls from a cache of recently generated content. Or, if things are really bad, it drops to base fidelity.
Which is
Right.
no LLM at all.
No LLM at all. The imagination layer gets bypassed, and the system just uses pre-authored templates. The world might get a bit more dull, more text-based, but because the physics layer is still running, the rules of the world don't break. Your inventory is safe, the logic is sound.
The world never loses its state. That's the ultimate failsafe. And it's all built on a modern web stack, TypeScript, HTTP, serverless. It's almost mundane technologically.
And that's the point. You don't need some exotic new stack. You just need to apply these neurosymbolic constraints using the tools we already have.
Okay, let's talk about the applications they built to prove this out. The versatility here is pretty stunning. Maybe we can start with the two Atlas systems.
For sure. The Infinite Travel Atlas was their test for grounding the AI in real-world data. The goal was to make an explorable Earth without a massive backend.
So the flow is simple. User picks coordinates on a map.
And the physics layer, the code, looks up the real geographic data for that, point, climate, altitude, that kind of thing.
And then the LLM generates a rich travel guide based only on that data. So Nairobi generates a desert bloom theme, and Honolulu generates an urban pulse theme. And it's all consistent because it's grounded in real deterministic facts.
Exactly. Then they took that same idea into pure fiction with the Galaxy Travel Atlas.
Right. This proves it works, even if the underlying physics are totally made up.
In this case, the physics layer uses procedural noise functions to generate the entire universe, structure galaxy layouts, star lanes, risk profiles. It's all deterministic code.
And the LLM just fills in the details like the ship's logs and the lore, but it's constrained by that TypeScript interface. So a planet at certain coordinates will always be a stormglass biome. The LLM can't just change its mind.
The constraints are what make it feel stable and real, even though it's infinite.
Let's switch gears to a game, AI Spire. This seems like a real stress test because games need to have unbreakable rules.
Absolutely. The core mechanics, HP, energy, all that are pure deterministic code. That's the physics layer. The LLM can't touch it.
But it gets to design new cards, right, through this wish mechanism.
Yeah.
That sounds risky. What if a player wishes for a card that says, I win the game?
That's the clever part. The LLM doesn't output game logic. It outputs a structured JSON object. It has the card's name, a cool description, and most importantly, a list of pre-approved effect codes.
So the LLM can come up with the flavor text gain incredible strength, but the code only understands the effect code plus combats TR.
Precisely. The LLM's creativity is translated into a controlled vocabulary of rules. It can't invent an exploit because the symbolic core won't execute it.
Okay, that's a very clean solution. What about AI alchemy, the self-expanding sandbox?
This one is fascinating. It's like those old falling sand games, but it learns. When two elements touch, the engine checks a reaction cache.
If there's no rule for, say, life plus fire.
Then it queries the LLM. The LLM synthesizes a new schema-constrained outcome like ash. That new rule gets instantly cached and added to the physics layer. The world's complexity literally grows on its own.
That's amazing. And they have an AI supervisor to stop it from going off the rails.
Yeah, another AI that watches the global state. If one element starts to take over the whole world, the supervisor can step in, maybe make it rain to add more water, just to keep the sandbox interesting.
It's incredible how many layers of control they've built in. Let's touch on the 3D one, Cosmic Voyager.
This shows how WWM integrates with a graphics engine. The physics layer handles the scene layout, orbital speeds, distances, all the math that keeps planets in their orbits.
And the imagination layer is like a real-time narrator.
Exactly. They call it the Cosmic Guide. It's a subtitle strip that refreshes every 30 seconds, and the LLM's narration is tailored to your specific camera view and what you're looking at. It's a great example of context-aware generation based on a fixed spatial state.
And finally, WWMpedia, where the world is just knowledge.
This is a really smart take on Argy. You give it a query, and it generates a whole Wikipedia-style page on the fly.
But the structure, the title, the table of contents, the layout, that's all handled by the deterministic physics layer code.
Right. The LLM is just responsible for the composition, for turning a pile of retrieved facts into a readable, structured article. It's forced to pour its creativity into a rigid, predefined scaffold.
Looking at all these examples together, from games to encyclopedias, it's just such a powerful validation. The WWM really feels like that practical, scalable middle ground we've been missing.
It does. And I think for anyone listening who's a developer or an engineer, the big takeaway is that our standard web stack TypeScript, JSON schemas, serverless, it's not just for websites anymore. It's a perfectly good, scalable substrate for building these controllable, persistent AI worlds.
Which is exciting. It means we can start building bigger, more complex things without constantly worrying that the whole system is going to collapse into hallucinated nonsense.
Absolutely. And it leaves you with this final provocative thought. If deterministic code can provide this unlimited state space and guarantee structural certainty for agents, what does that mean for future really complex multi-agent simulations? The places where memory and non-determinism have always been the biggest blockers. Maybe we should stop thinking of LLMs as just predictors and start seeing them as constrained imagination engines inside a much larger symbolic system. That tight integration might just be the key to building the kind of reliable, open-ended worlds we've only ever dreamed about.